Okay, so just like we learned our basic rules of differentiation and then we kind of took it up a notch with our chain rule, today we are going to we've learned our basic rules of integration and we're going to take it up a notch with using something called U substitution. So that being said, we are going to jump into 4.2 guided notes, which is U substitution 1, and U substitution 2 is coming, and maybe even 3. Haven't decided how many parts I want to break it into, but I do want to keep things in manageable chunks. So do chapter 3 test, homework, problem set 4.1, 4.2. Lecture will be linked, obviously, when it is done. So introduction. Consider the problem, the integral of x minus 4 in terms of x. In order to integrate this, we might break up the function such that we can integrate each piece separately and apply the power rule for integration, right? We take the integral of x dx minus 4 times the integral of dx. Nothing too crazy. We can do that, no problem. Now, say that we were asked to integrate the similar yet different function f of x equals x minus 4 quantity squared. So what is the difference between x minus 4 and x minus 4 quantity squared? And then what is the difference between taking the integral of those two functions? Hopefully you thought about that for a second. And you realize that the integral of x minus 4 quantity squared has become a composite function. And composite functions, we know, kind of throw a wrench in things, right? With differentiation, we had to use the chain rule. And so now that we're undoing differentiation, we need to undo the chain rule. And I'm getting ahead of myself, but given our current knowledge of integration, in order to find the integral of x minus 4 quantity squared, we would first expand x minus 4 and then integrate accordingly. So this is something that we could still solve, right? Because we know that x minus 4 times x minus 4 equals x squared minus 4x minus 4x plus 16, which is x squared minus 8x plus 16. So we could take the integral of x squared minus 8x plus 16 dx. And then using our basic rules, we know that the solution would be x cubed over 3 minus 2x squared plus 16x plus c. Okay, so it's a little bit more challenging, but we still can do it, right? Using our basic rules, we just have to expand it out. What if instead our function was x minus 4 to the 4th? Suddenly this problem feels like it's a lot more trouble than it's worth because we'd have to first expand x minus 4 to the 4th, which could get very algebraically messy, and then apply the power rule of integration for each piece of the function. So let's think about this in terms of something we're more familiar with, and that thing being the chain rule. Oh my God, I ruined it. So if we were asked to take the derivative of x minus 4 quantity to the 4th, we would use well, I just spoiled it, but we'd use the chain rule. And therefore, if integration undoes differentiation, and we're looking for a way to integrate the function x minus 4 to the 4th, then we need to know how to undo the chain rule. So the shortcut method for integrating these types of problems is called U substitution, also known as your new best friend. You're going to use it all the time. And the key to solving integration problems using U substitution is just recognizing certain patterns, okay? So in order to comprehend how we're going to undo the chain rule, it's useful to recall the formal definition of the chain rule. So f of g of x is equal to f prime of g of x times g prime. And in order to undo the chain rule, apparently undo is one word, we will use something called the U sub. So consider our example from above. The integral of x minus 4 to the 4th dx. Rather than going through the tedious process of expanding the binomial, we can simply use U substitution to take the integral. So this is kind of like fitting together pieces of a puzzle. So let U equal x minus 4, okay? And then we're gonna look down one. So there's 3 things we need to find, but they all build off this one thing of letting U equal something, right? So you're gonna look at your problem and you're gonna determine, okay, I'm gonna let U equal x minus 4. And you'll see why once you see the process. Du refers to the derivative of U. So whatever you let U be, du is the derivative. So the derivative of x minus 4 is 1. And then, since we are taking the derivative in terms of x, we're going to add 1 dx. Okay, so du is going to be the derivative of whatever you let u equal to be, and then you're going to multiply by dx always because, okay, I'm in terms of x. And then this last blank, it says dx, and you already have dx right here. And so this dx down here is the same dx. So since you know du is equal to 1 dx, then you know that dx is going to be equal to, well, you don't actually even have to solve. Like maybe you'd have to divide by 1, but that doesn't do anything. So we know that du is equal to, or dx is equal to du. Okay, so now we're going to look at our integral. We have the integral of x minus 4 to the 4th dx. But now we've done some fancy things to rearrange this. And we've made this into the integral of x minus 4 has become u, still to the 4th power, and dx we know is equal to du. So remember, when we integrate, the variable in our integration problem has to match that du, dx, ds, dt at the end. So we have a variable or a problem, a function in terms of u, and we have du. So we can integrate this. We can just go ahead and use the power rule, right? So u to the 4th du is equal to u to the 5th over 5 plus c. And now, literally, the final step is that u is equal to x minus 4. So our answer is going to be x minus 4 to the 5th over 5 plus c. Okay? So this seems foreign at first, but take it slow, one step at a time. We're going to get through this. We're going to become masters at u substitution, and literally you are going to use it all the time. Okay? So, examples of u substitution. I got a little wonky, but I think it fixed. Okay, so number 1, number 2, number 3, they're kind of similar to the ones we just did. 4, 5, and 6 are a little bit trickier. So I'm going to take you through 4, and I want you to try all of these problems before we come back to class. And we will take class time to do all of these together, but I do want you to try it on your own because me walking through it is not as effective as you actually like struggling through it on your own and building those connections and figuring out what makes sense to you. But we are going to do number 4. So I'm going to let u equal x cubed plus 1. And as you become more comfortable with u substitution problems, it will become more obvious about what you want to make u equal to. And we will also talk about this in class tomorrow, or not tomorrow, on Tuesday. That's not tomorrow. So we're going to let u equal x cubed plus 1. The derivative of that is going to be 3x squared in terms of x, so I'm going to add that dx. And now, see, I have to do something a little different because du is equal to 3x squared dx. And now I want to solve for dx, so I'm going to have to divide by 3x squared. So I know that dx is equal to du over 3x squared. All right? And now I'm going to plug that back into my integral. So I'm going to have the integral of 3x squared times the square root of u times dx, which is equal to du over 3x squared. And now you will conveniently see that 3x squared over 3x squared cancels. And so you are ended up taking the integral of the square root of u du, which is equal to the square to u to the 1, the integral of u to the 1/2 du. And then I will leave that up to you to use your power rule and substitute back in what u is. Okay, but u substitution is like a puzzle, okay? So think about all the different pieces that you need to put together, like basically just finding u, then the derivative, and then solving for dx based on your derivative, and then putting that back into your initial one, and then it kind of like magically comes together and you have an answer. Okay, so I want you to work through these 6 problems on the notes and also the web assign, and we will go over this in class. Bring any questions you have, and other than that, have a lovely day, and I will see you in